in some sense, I always feel that astrophysicists have all sorts of advantages, and one is that they just have much prettier pictures than particle physicists usually do. And this, of course, being one of them. I mean, do you all sort of recognize what this is? Okay. Really? Okay. Yeah. Well, so this is actually, I mean, it is a picture of the, it's a picture of the Crab Nebula taken through the Hubble Space Telescope. It is supposed to be an example of a core collapse supernova that happened about 1,000 years ago. Okay. I'll get to that in just a second, but in any case, yeah, just like that as a picture. Okay, so what I'm going to talk about, I mean, just basically 3 chapters. First one is, what is a core collapse supernova? And what do neutrinos have to do with them? Okay. In some ways, it's kind of related to, why is a particle physicist waiting for something in the sky? You know, to explode. Why am I waiting for something to explode? Second chapter is, how do we actually detect neutrinos? And then the third is, what are we doing, in some sense, as we wait for the next core collapse supernova in the galaxy? I should make that qualification, in the galaxy, because these things are popping off all the time, but they do tend to be a little bit rare. So it is a little bit of a waiting game. Right, okay, so first chapter. What's a core collapse supernova, and what do neutrinos have to do with them? So here we have, well, a couple things. So here's that picture again. Well, it's actually not that, the picture that I showed in the very beginning, but gosh, do we actually have a pointer here? Okay. Something green, right? So there's a tiny green dot, which is not very noticeable. Anyway, so this is the Crab Nebula again. I think taken, lower resolution some years before. And as I mentioned, I mean, this is actually something that happened about 1,000 years ago. We think it was 1054. There is only a little, I mean, there's a little bit of controversy about that, but not too much. It is actually, I mean, one of the things that's quite notable about supernova in general, actually not just particularly with core collapse supernova, is that they are among the brightest things that actually occur in the sky. Okay, so the one here, 1,000 years ago, this probably lit up the sky. Well, in fact, I don't remember if actually the number 23 days. So visible during the day for 23 days and at night for 2 years. That may actually come from the records, from historical records of what describing the supernova. I think that must actually come from the historical records. And we actually have quite a few historical records of this kind. The most detailed ones, I think, are the ones that come from China around that time. And from that, from the characteristics that are described, people sort of infer that this was what we call an electron capture core collapse supernova. It's just a particular kind of thing that happens. It was quite dramatic. So I think there are records, there are records from China, there are records from Japan. Arguably, we may even have paleoglyphs in North America, and I think also Australia, which might refer to them. One of the few places that doesn't seem to have very much of a historical record of this is actually Europe, even though it would have been quite noticeable. Though there's controversy about that. Sorry, I just find this really quite fascinating. I guess I do have a little bit of a historian in me as well. People still publish papers, so you can actually see right here, there was a paper just a few years ago where they said, oh, well, actually, maybe there are references in European records to this supernova, which should have been very noticeable. But it was, I mean, they were a little distracted that year because that was also the year of the schism between the Western and Eastern churches. So there was kind of there was a lot of stuff going on. But they point out that there was, on this coin that dates from that period of time, there's this big bright thing there. And they say, oh yes, maybe this is a reference to a bright thing going on in the sky. Anyway, Now, as bright as these things are, as I said, visible during the day for 23 days, so that's in spite of the sun being up there, that's actually a tiny fraction of the energy that's released in these particular events. The core collapse supernova is actually expected to be driven mostly by neutrinos. So 99% of the energy is actually emitted in neutrino form, not in terms of visible light. Okay, so all this stuff, I mean, that bright flash in the sky, it's not even, I mean, it's just a tiny bit of the energy coming out. Now, the process that we're talking about, for this core collapse supernova, I'm probably standing on the wrong side of the microphone here.
Okay, we'll say it if you want.
Yeah, that's a good idea. Yeah. Somehow it feels a little bit more natural to stand on that side. I don't know why. Okay. Right. So this cartoon is kind of a description of what the sort of canonical model of a core collapse supernova is right now. You have supposedly a red supergiant star. Okay, so this is quite an old star, generally quite massive. And by the time that we start talking about a core collapse, it has already burnt up a significant amount of its fuel. So you have increasingly heavy elements developing in the core. Eventually, these things are actually burning pretty much from silicon. I think silicon is like one of the very last stages, and you get up to iron. And of course, iron is from your actually, how many people here are third year and have done, third or fourth year and have already done the particle and nuclear physics? Right. Okay, a few of you. In any case, so at a certain point, you get to the more stable heavy elements, such as iron, okay, and you can't really burn more than that. So that's the point at which the outward pressure, the radiation from all the fusion going on, is unable to sort of push out against the gravity, which is actually pulling everything back in. Okay, so when the fuel starts giving out, that's when everything starts contracting. And if it's particularly massive, it'll go through, well, it's actually quite a rapid collapse. Actually what ends up happening is that you've accumulated all these, you've made all these heavy nuclei. You actually then go through a process of basically rapid disassembly. So all these heavy nuclei essentially get converted, or many of these heavy nuclei get converted essentially into neutrons. Okay, and this is the step onto the formation of what we call the proto-neutron star, which eventually sort of coalesces down to a neutron star. But that process is where you get a huge burst of neutrinos coming out. Eventually, of course, you enter that other phase, right? So you've gone from your sort of basically your iron core, where you still have individual atoms, and then you go down to this nuclear stage where you have the neutron star. That actually generates a shock wave, which then propagates out. It was thought for a long time that shock wave then produced the explosion, but actually I think within about a year of that mechanism being proposed, people realized that there was actually all sorts of stuff going on. Because while you have a shock wave coming out, you still have matter coming in. And there's actually so much friction and so many opportunities for energy loss that essentially the shock wave, whatever happens, tends to stall. Okay, so this is actually one of the first problems that people ran into when trying to come up with models of core collapse supernova. We knew that these things happened, but how do they happen? Basically, whenever we tried to model anything, these explosions always just kind of petered out. Because the shock didn't really go anywhere after a while because it just lost all of its energy. So what people think right now is that the neutrinos have to play a critical role in actually somehow accumulating behind that shock wave and eventually bursting through. Okay, this is a pretty extreme scenario. Just to point out one interesting fact, for this to work, and this actually is. It is actually plausible in this case. The matter is actually, accreting so quickly, and the matter is actually so dense that actually for a while, it's expected that the neutrinos can't escape. In other words, neutrinos, which normally you think of as just flying through anything without really paying any attention at all, right? Because neutrinos only interact, actually, I'd probably better have said this. How many people know what neutrinos are? Okay, you got an idea, right, okay. So, key fact, neutrinos only interact with other matter through the weak force, okay? So, the interaction cross-section is extremely small. So normally, you know, we can be generating neutrinos in fact, in a nuclear reactor on Earth, and we can actually be detecting those. They'll just like fly through the Earth's crust, and we'll detect them in a detector several hundred kilometers away. Okay, you know, generally we don't, and in fact, you only get a few of them. That will have some consequences, which we'll get into in a bit. But yeah, you know, these neutrinos just have a tendency. I mean, as far as the neutrinos are concerned, the universe is essentially transparent, except in this circumstance, right? So that's how dense the matter is that we're dealing with. Okay, so you get all sorts of weird physics that potentially goes on, and eventually, yeah, the neutrinos finally do break through, and then you get this huge, shock breakout. And that's actually when you start getting things like, well, if the shock is revived by the neutrinos, that's when you get the explosion and all the light coming out that brightens the sky. Otherwise, if you don't, then, well, you might get just a neutron star left over, but then another possibility is that you actually form a black hole. Okay, now I won't spend so much time on single slides after this. Okay, so anyway, so going through those different phases, and people have done a lot of computer modeling. This is just a snapshot of one of the, actually a three-dimensional model. And yeah, there are groups that just pretty much just spend their time coming up with computer models of these things. One of the outputs that they have is sort of neutrino luminosity as a function of time, and this is log of time, so that's why 0 has to be missing there. So this is where the t equals 0 is that bounce where the basically you hit that phase transition, and you know the nuclear matter can't get more dense. At that point, you will get your huge burst of neutrinos, and you see here different neutrino flavors. Okay, so you have your electron neutrinos, electron antineutrinos, and then other, the muon and tau neutrinos as well. And yeah, this is where you're seeing the sort of 99% of the energy coming out. Then you also have gravitational waves. Those guys are also coming out. This is a little bit, people are a little bit uncertain about this. Or actually, no, we're pretty sure that there will be gravitational waves. Of course, to have gravitational waves, you have to have, you have to have at least a quadrupole moment, right? So you have to have something that's quite asymmetric about the explosion. It turns out that this is actually key to the explosion as well. Anyway, so I guess people now sort of have this feeling, yes, there should be gravitational waves, but we don't know what the waveform should really look like, because there's a lot of complex dynamics in this. Notice that the electromagnetic radiation still hasn't really come up yet. Okay, and that may come up within 30 minutes to about 48 hours. That's the expectation, after all the neutrinos and the gravitational waves come out. Okay, so that's where all the, this is the shock breakout, and then plateau, and then the typical sort of electromagnetic light curve that comes out from a core collapse supernova. I should mention also, just before I go on, so that's actually, this is the supernova burst. This is what we often refer to as the supernova burst. There's also this last phase, just before the supernova. The expectation is that as you're getting these sort of increasingly heavy elements, the neutrinos will also, the neutrino luminosity will, it's still quite low compared to the burst, but at least it's increasing, and quite dramatically actually towards the end. And at least for nearby stars, nearby red supergiants, we might actually just about detect some of those events before the burst. And that can actually be extremely important in terms of understanding the physics. Okay, now, what can we learn from core collapse supernovas, right? And it's not just that we're going to sit around waiting for a neutrino burst. We also want to learn things from it. Now, this slide is an extremely biased slide, I'll have to say, because I'm saying, oh yeah, there's a lot that we can learn from for particle physics from the supernova burst, such as neutrino masses and mass ordering. There are a lot of different ways in which we tackle this, but this is actually, but they're all difficult. Actually, it turns out that the most intense neutrino burst in the universe gives us very good information, or potentially gives us very good information on this. Also, dark matter. Whether there are sort of particle versions of dark matter out there, they would probably be generated or at least interact with the supernova. Non-standard neutrino interactions. Remember, these densities are things that we just don't see on Earth. Okay. And there's been a lot of discussion about fast flavor conversions. Hadron quark phase transitions. This is when you get down to the neutron star, that's kind of like a nuclear state of matter. But it may turn out that there's another state of matter even more dense than that. We just don't know yet, okay? Because we've never seen things, sort of so up close at that kind of scale. There is also, some people think that we can get something about proton spin from the component of proton spin that's attributed to the strange quark. I'm a little bit more skeptical of this one, but anyway, people certainly do discuss a lot of fundamental particle physics questions that are addressed if we just get these supernova neutrinos. Right, and this is the bias. I just have a single bullet point that says there's also a lot of astrophysics here. Okay. Now I have to admit, I'm not an astrophysicist. I'm, not, just sort of personally, I guess I'm not quite as interested in sort of the particulars of one exploding star as to whether it had so much, circumstellar material accreting onto it at this particular rate. To me, I want to know more about the general properties of these particles. So, that's just a personal bias. People do get very excited about all these different aspects. Exception is black holes. Black holes are basically like really big particles, as far as I'm concerned. Okay. Anyway, there's also, kind of something where these two things actually cross, both the particle physics and the astrophysics, is something called the diffuse supernova neutrino background. So I said that, these core collapse supernovas are actually quite rare in the galaxy, but of course there are a lot of galaxies. So, basically in the, if you're observing a decent section of the universe beyond the galaxy, then you actually see quite a few of these things going on all the time. So I think like the telescope, which is actually turning on right now in Chile, called the Vera Rubin Observatory, they are expecting to see, I think so over a 10-year campaign, they're expecting to see 1 million supernova, about half of them core collapse, every single year. Okay, but you can see a lot farther in the optical than you can with these neutrinos. Okay, anyway, but the thing is that these neutrinos, once they leave the supernova, they're just flying around the universe. So you can actually integrate all the, sort of like all the supernova neutrinos from all the supernova going around, the universe, and, and you could say, well, how many of them do we see on the Earth itself? And you can calculate what that should be. We still have not observed this yet, okay? But this can also tell us a lot, especially if there are features in this background, in this energy spectrum. This can tell us a lot about supernova, even if we have not seen a supernova in our galaxy. And this is just kind of an illustration of where these things sit in terms of energies. So this is, I guess, MeV. Okay, that's not a million MeV. That's actually just MeV. So kind of nuclear energy scales is what we're really talking about when it comes to supernova. That's the burst. Quite a bit lower down here is the background from old supernova. Okay, that's what we're talking about, the diffuse supernova neutrinos. Okay, and then there are a whole bunch of other interesting neutrinos up there. Okay. An example of new physics, sort of new particle physics from core collapse supernova. I talked about dark matter. The argument usually goes something like this. I mean, there are a lot of people who sort of, it's almost like a little cottage industry of sort of dark matter models and what they would do to a supernova model. So if you have the on-center model particle physics that's coupled to neutrinos, so dark matter that actually interacts with neutrinos, through some gauge boson or whatever, you would actually expect, or there would be an expectation that dark matter, being largely inert, but still interacting gravitationally, will collect in the center of these big massive stars. Okay, so then the question is, what happens if the star explodes? Okay. And this can have several different effects. I mean, right, because of the, if you have these new particles sort of in the middle of the star, that may actually change the way the burst comes out. It may change the energy spectrum. Also, just because of the coupling, these particles will come out with higher energy than the neutrinos, because presumably their interactions are even less probable than neutrinos. And then also you even have decays in flight, because if you have neutrinos that can make dark matter particles, you can also have dark matter particles decaying to neutrinos. Anyway, so a lot of papers that go along these lines, and so even if we see one of these galactic core collapse supernovae and we see the neutrinos from them, just publishing the energy spectrum of the neutrinos we see is going to actually set off a lot of papers. Okay, and just as kind of as an illustration of that, the last galactic supernova that we saw was 1987, and I'm going to show you the data from that. And I would say that even yesterday, there was basically there's always a constant stream of papers that say, yes, we have a new discussing new physics. What does supernova from 1987? What do the neutrinos from there say about it? Okay, and people still do a lot of physics with that one supernova. Okay, right. Should mention, I gave you sort of a canonical picture of what happens with core collapse supernova. They're not all alike. Okay, and yeah, even just with different computer models, you will see some of this variety. So let's see, I think, I have several different examples here. So of course, there are variations with the progenitor mass. Okay, so here you have, this pointer is not very good. So you have 40 solar mass, you have, actually, just remembered, I think you can see the mouse, that might actually be better. Right, so you have 40 solar masses here, and then you have 75 solar masses, and yeah, you do get more energy that comes out of the more massive star, not a huge surprise. There are some extra features like what they call the standing accretion shock instability, so that you might be able to see in terms of in time. This is actually essentially waves going across basically sort of setting up matter waves that go in a particular direction as a black hole is forming. So that's kind of intriguing, something that if you have the time resolution and enough data, maybe you would be able to see. Sometimes you would actually see a long accretion. Okay, now so long accretion basically means you have matter falling in for much longer than you would normally expect. The reason why this might happen is fairly simple. The system might be rotating. Okay, rotation has massive effects on all these things, but of course, most of the models that people tend to run are nice and stationary. Okay, it's just it's simpler to calculate. But anyway, so that sometimes happens, and usually what happens as a result of the long accretion is that the neutrino luminosity keeps on going up, and then when you pass a certain threshold, like you go over a critical mass, you might have a black hole form, in which case you get an abrupt cutoff, which you can see there. And these kinds of things with hadron quark phase transitions, you might actually see secondary bursts. So there are a lot of different features that you might actually see. Okay. Just on the note of black hole formation, there was, what would you see if a black hole formed, right? Well, you're not going to get, or at least the expectation is you're not going to get the bright light in the sky, because the black hole basically, sucked it all up. Well, it didn't really suck it up. That's not a good way of saying it. But basically, the explosion failed. Okay, so people have gone out and looked for stars which just disappeared. And there have been a couple of these candidates. So we actually have, so here's a picture of one of them that I guess was found like 2014 or something. Well, the disappearance happened in 2014. This, I think the distance is about, I don't remember what the distance is. Darn, I just looked this up yesterday just to check. Oh, no, I do have, okay, I have it written there. Yeah, so 7.7 megaparsecs, which is, quite far out of the galaxy. And we also have a disappearing star candidate in our neighboring galaxy, M31. So this is actually 700 kiloparsecs. Okay. Just in case you're wondering, the radius of our galaxy is about 30 kiloparsecs. Okay. So these are candidate black hole formation events, and people have gone and looked for neutrinos coming from them and so forth, and so on. This was a side little project. I'm just, shameless plug of my own paper, I have to say. So yeah, at one point my student and I, we were looking into some of this stuff with the black hole formation, and we realized that a lot of the simulations, a lot of the papers, when they talk about an abrupt cutoff, the reason why it looked like there was an abrupt cutoff is just because the simulation ended, because the approximations weren't valid anymore. Okay, because you're always doing these numerical approximations, and then it's like, oh, you need general relativity. Okay, you got infinities and other sorts of problems showing up. We just end there. So there was this question as to, okay, how sharp should this cutoff really be? And it turns out, first of all, you can do an evaluation, relatively straightforward evaluation using general relativity, and you get a characteristic time constant of about, square root of 27 times the mass of the forming neutrons, the forming black hole, actually. That result actually turns out, like many of these kinds of results, was calculated first by a Russian in 1963. Okay, because it almost seems like every time you want to do a new calculation, someone in Russia has done it before, several decades before. He did make a little mistake, and that was corrected by Kip Thorne a few years later, and he translated the paper as well. And so that result for a non-rotating black hole has been around for a number of years. So my student and I, we sort of sat down and thought, okay, what happens if you get a rotating black hole? And more interesting things happen. The time constant actually can draw out considerably, but it's still within about 0.1 millisecond. Okay, so it's still happening very quickly. It's just, you would need more data to be able to discern whether there's a non-zero time constant there. And you can get all kinds of weird little effects like neutrinos coming out, and then just because of the effect of general relativity and the fact that the frame is actually dragging by the gravity, the neutrino will come out in this direction, it'll sort of like, and then be kind of turned around and whipped around, which is kind of fun. Yeah. Anyway, so, I'm an experimental physicist. We just get into this kind of stuff just for the fun of it. Okay, right. How do we detect neutrinos? So it's fine to say, okay, neutrinos come out, there are a lot of them, but how do we actually detect them? There are two main channels that I'm going to talk about. One is what we call elastic scattering off of the electrons. This is actually one of the more important ones. If you like Feynman diagrams, here are a bunch of them, right? So leading order Feynman diagrams for the scattering. You're scattering off the atomic orbital electrons in your detector. Okay, so you get your incident neutrino coming in and then exchanging a Z boson, virtual Z boson, and then these things leaving with different division of energy. Of course, this being a Feynman diagram, you have to add up all the potential contributions. Okay, so you end up with a few more diagrams, at least in the case of electron neutrinos, right? For exchange with Z's, actually this is not, so do this in the right order. So with the W's, this actually has to be an electron neutrino, okay? For Z boson exchange, or what we call neutral current interactions, the flavor of the neutrino can really be any flavor. Okay, so electron, muon, tau neutrino, et cetera, and it doesn't actually matter. Now the way that we would see these events, okay, because basically you just have your electron coming in, and you had your well, you had your neutrino coming in, you had your electron, which was relatively speaking at rest. That electron gets kicked out somewhere. The neutrino goes away, you still don't see it. Okay. So you can only pick up the energy of the electron that got kicked. And the way that we oftentimes do that is that, especially if you have a big water detector, the electron will actually be going faster than the speed of light in water. And when that happens, you get sort of like the light version of a sonic boom. So we call this Cherenkov radiation. Usually kind of high wavelength. It's actually also why if you see photographs of nuclear reactors, there's always this kind of eerie blue glow. That's actually the Cherenkov radiation coming from the electrons being scattered. And so yeah, you get this shock wave. Now the electron does get reabsorbed, so it only travels maybe 10 centimeters or something like that in water, and then the Cherenkov light stops getting emitted. So what you end up with is a ring. Okay, so this is the snow detector. This was out in Sudbury in Canada. So it's deep underground, and so you have this. Well, we had very pure water inside here. Actually, it's quite pure water outside as well. It's surrounded by a lot of very sensitive photon detectors, and the photon detectors, which these are the hits of the photon detectors. So you see this very distinct ring pattern. And that enables you to sort of point back to the sun. You can actually say, okay, these neutrinos probably came from the sun. And this was actually pretty much key in actually establishing neutrino oscillations, okay, back in the early part of the century. Okay, so 2015, two experiments, Snow and Super Kamiokande, shared the Nobel Prize for that discovery. Okay, the other one, so that was based on electron elastic scattering. The other one is called inverse beta decay. This one, the Feynman diagram is shown here. Now this one is specific to the electron antineutrino interacting with protons. Now remember, in water, you do have a lot of protons sitting around. They're called hydrogen atoms, right? So sometimes you will get the interaction with the proton. It gets converted into a neutron. Now the neutron, of course, will not be bound to whatever it was bound to before. It'll go wandering off. And so what you see is that the electron coming in, interacting with this proton, turning that into a neutron. In the process, you get a positron coming out. Now the positron you can detect using those techniques of Cherenkov radiation, so forth and so on. But then the neutron goes, as I said, wanders around for a while, thermalizes, eventually gets absorbed by another proton to form a deuteron. And that has a characteristic energy. It emits a photon of about 2.2 MeV, right? Okay, so this kind of thing does happen. It's a very high cross section, so this is a very important reaction to look for. There's another variety of this, which is that if 2.2 MeV is not enough for your detector to actually detect, then you do things like dissolve a lot of gadolinium in your water, and these guys they have a high neutron absorption cross section, and they emit not 2 MeV but 8 MeV, much easier to detect. Okay, so some water detectors, in particular the Super Kamiokande detector, has actually done this, and they are coming up with great results that take advantage of this. Okay, other interaction channels, because as I like to say in particle physics, whenever you hypothesize that something happens, you have to take into account that everything happens. Okay, you cannot really just hypothesize one interaction and only that one thing. Okay, everything that is implied will also have a probability associated with it. So there are a bunch of these other interactions which we want to look at. Sometimes they are also backgrounds to the signal that we're looking for. Okay, that'll come up later. Okay, I said that I was going to show you what the data from 1987 looked like. This is one of the experiments that picked up neutrinos. So we had several neutrino detectors going on at the same time. This was, Kamiokande, actually it stands for the Kamioka nucleon decay experiment. They were actually waiting for protons, proton decay, okay, but also detects neutrinos. And this spike, very noticeable, okay? So, normal sequence of events. Now this supernova actually is in Large Magellanic, I always have trouble pronouncing that, Large Magellanic Cloud, so that's 50 kiloparsecs away. And yeah, so these neutrinos are seen, and 2 or 3 hours, this bright light was actually seen. Now in this case, it didn't get seen everywhere in the sky because it's 50 kiloparsecs away, okay? So, you know, too distant. And yeah, many years later, people are still looking at this, right? This is the Hubble Space Telescope in the 1990s, and you know, you can actually see the structure coming out of this explosion. Quite dramatic structure, actually. Now, I should say that a couple notes on this. The fact that this was observed 2 or 3 hours later is a complete accident. Okay, it just happened that some guy, a couple people, but in particular, I think it's this Albert Jones in Australia. Just, you know, they regularly like to point their telescope at this Magellanic Cloud, and they just happened to see that there was something different. Now, the other distortion in the slide is that the order is completely wrong in terms of how these things were actually found. Okay, because of course no one was looking at this data at the time. This got, you know, the word about the supernova came out, and by this time in the actually the discussion about what would happen in a supernova and what would happen with supernova neutrinos actually happened in the early 1980s, so this was very convenient. People went back and looked at their data, and lo and behold, there's a huge spike. Okay, so this is actually the post-data process. Okay, it wasn't actually discovered this way. The other thing, which is kind of funny, I mean, okay, so there are 3 detectors which picked up these events. This is all the data. Now remember I said, people are still publishing physics results on the basis of 24 events that happened back in 1987. Okay, that's how important these things are. And that's how valuable the supernova neutrinos are. So yeah, so these are the Kamiokande events, and then there was IMB, which is up in Michigan, I think, and then Baksan, which is in Russia. Yeah, again, here's another little lie. When you look at these, you know, these things, they kind of nicely sit on top of each other. That's kind of people's best guess, right? Because actually back then, people didn't really think of synchronizing all the clocks. Okay, so you see uncertainties here, right? 1 minute, plus or minus 1 minute, plus or minus 50 milliseconds, et cetera, et cetera. Even that's probably overstating the accuracy. I think at least in one case, one of these experiments actually just pretty much completely lost the timing information. So the actual absolute time of the observation cannot be reconstructed. Okay, but on the other hand, burst of neutrinos like this doesn't happen very often, so chances are they're pretty correlated. Okay, right. Good news about modern neutrino detectors is that they are much bigger and much more capable than back in 1987. It's also a lot easier to synchronize clocks across the globe. It's not trivial, but with global positioning satellites, it is so much easier nowadays. Synchronizing things to about 1 millisecond or 0.1 millisecond is actually not too difficult now. So we're going to go through some pretty pictures. So this is Super Kamiokande. Just for scale, that's a truck. Okay, so he's kind of big. It is under a mountain. They basically had, well, you know, a lot of times these underground detectors, you know, they start off as actually old mining sites. Okay, Kamioka is an old mining town. This is a picture inside. So yeah, you know, you got big cavern, right? A lot of these photomultiplier tubes. And then, you know, you fill with ultra pure water. And actually, one of the easiest ways to do anything with the phototubes is actually just to, you know, while you're filling, just float a boat out there and go and sort of like visit all the PMTs along the way. So that's one experiment. There's another one that is actually under construction right now, which is planned to be 5 times bigger than Super Kamiokande, so they're essentially hollowing out a mountain. And I mean, this is really impressive. Okay, similar location. Okay, but you know, with 5 times more volume, With the interaction cross-section, that means you just have more things to scatter off of. We could actually see the neutrinos from a supernova in Andromeda, which is pretty cool. Actually, even Super Kamiokande claims that they should be able to see a few events, but it may be a little bit difficult to distinguish. Right, if you want to go even bigger, now this would not be in water, but you could use the very nice transparency properties of ice, ancient ice down at the South Pole. So that's what a bunch of people did. This is a big sort of 1 kilometer cube of photodetectors. And it is specifically to, it's what we call the neutrino telescope. It's mostly designed actually to get the really high energy neutrinos, like TeV, 100 TeV, something like that. With a supernova, it looks very different, but this would actually be quite an important supernova neutrino detector as well. And of course, the other cool thing is that you get to go to the South Pole. But you do have to get all your wisdom teeth extracted before you go. I remember that because a colleague of mine had to do that. Related to that is another experiment called KM3Net, which is sort of like, well, we don't really want to go through the trouble of actually getting all the way down to the South Pole. Let's build it off the beach in the Mediterranean. Okay, much more pleasant. This one is they're still adding to it. And so, they have these optical modules with the photodetectors, just kind of like in strings, quite deep in the Mediterranean. It's one of the only detectors that I know where they actually have sort of like a, where they have to publish sort of a background component that just comes from luminous fish. Okay, not too many detectors will have to do that. They also got a nice record. Recently, they got the highest energy neutrino ever recorded. So I think what they're saying is, let's see, what is it? 220 PeV. Okay, this is quite a bit higher energy than anything IceCube has seen. There's some discussion as to why that, is or is not plausible. And of course, energy calibration is always a little bit of an issue. Now, going back much smaller. Now, those are all sort of water detectors, so they deal mostly with water Cherenkov. Cherenkov radiation. This is the experiment that I tend to spend most of my time on, which is Snow Plus, which is in Canada. It's about 2 kilometers underground, so it's one of the deepest detectors. And even though it might look large, it's actually quite small, compared to the other ones that I was talking about. Those are people. And what you're seeing here are the ends of the photomultiplier tubes, since obviously most of the photomultiplier tubes are facing inwards. This is what it looks like inside. Okay, so it's like the old snow detector, but instead of ultra pure water or heavy water, which is what was inside the snow detector, now we have liquid scintillator in there. Okay, so change up the detector medium, sensitive to different things. And just some pictures of kind of life in a. Well, if you had seen me lecture on B2, like last year, then you might have actually seen some of these pictures before. This thing is actually the. Actually, you see this chimney here. This thing is sitting right on top of that, so that's how everything gets into the detector. Because it is actually in a mine, it's still a working mine, you have to walk quite a bit to actually get to that. So you actually, you take a lift that goes straight down, takes about 3.5 minutes to go down, and then you kind of like walk for 45 minutes, and you have to be wearing mining gear. So I used to have mine safety training, and I had to dress up like this at 4 in the morning in order to do this. And of course, it's always very important to have pictures like this, because otherwise, you only see your lecturers wearing shirts and things like that, and don't realize that yes, we actually do put on the hard hat sometimes. This is the refuge. So if you ever have a little problem where like rocks start falling and they can't quite guarantee the safety and everything like that, they say, okay, go back to refuge and just kind of like hang out there for a couple hours. So actually, in this case, this isn't hanging out for a couple hours. They've probably just arrived and they are having their second breakfast, because if you get up at 4 in the morning to do this and you spend all that time getting down there, you're really hungry by the time you've actually gotten to the lab. And then this is our version of going in the boat. Okay. little bit more confined in that case. Related to SNO+, there's a much bigger version of it called Juno. So SNO+ is about 780 tons of liquid scintillator. Juno is 20 kilotons. Okay, so much, much bigger. Similar sort of idea though. Okay, and they are actually currently filling with the liquid scintillator, and they expect to be operating this by the end of this year. So it's coming up very quickly. This is a picture of their detector. I'm trying to look for something that shows any sense of scale. There's a stool that you can sit on, right? Anyway, it's really impressive. Okay, so that's those are liquid scintillator detectors. There are other nuclei that you can use. So for instance, you have the helium and lead observatory, which is also at SNO Lab, and this one is specifically sensitive to electron neutrinos, which is actually kind of useful to get these specific channels. This has been operating since 2010 and 2012. It's extremely low maintenance, and one of the consequences of this is that this detector may outlast all the other detectors, because basically there's almost no operating there is operating overhead, but it's a lot less than the other experiments. Okay. On the other hand, you sit there staring at a big brick of lead. Okay, which is, I have to say, not quite as exciting. Okay, so let's see. What happens with the next galactic core collapse supernova? Right, so the bad news is from a survey of historical records and nearby observations, massive stars, neutron star birth rate, other sort of things like various isotopes of aluminum. People have gone and calculated the rate of a core collapse supernova in the galaxy, and it comes out to 1.63 plus or minus 0.46 per century. Okay, so you might say in my career, the probability of it actually happening in my career probably kind of on the small side. On the other hand, for people just getting started out doing physics, there's a decent chance it'll happen in your career. Okay, so things to look forward to. So they are extremely rare, but they're also extremely rich in physics. All those detectors that I showed you, and there are a bunch of other detectors as well, they're all actually designed to do something else. Okay, they're not, except for the HALO detector. The HALO is pretty much just a supernova detector. The other ones pretty much are, they're focused on things like nucleon decay, or dark matter, or neutrinoless double beta decay, which is what the SNO+ main purpose is. But if a galactic supernova happens, as people say, that's what everyone's doing. Okay, that's what we're going to spend time on, because there's just too much physics that's going to come out of it. But it is a race against time. As I said, hinted at before, neutrinos are the starting gun, and the amount of time that you have before the shock breakout can vary, as little as 30 minutes and as much as maybe like 48 hours. Okay. So, the race takes place once in a lifetime. You don't know when it's going to happen. You don't know how long it's going to last. So you just got to get all hands on deck, and basically every possible way of observing this, you want sort of focused on the sky to try to get as much information as possible. And that's where we have this SNOOS collaboration come about. SNOOS is it's a network of neutrino and dark matter detectors around the world. So that includes things, IceCube, Superchemicanda, Camland. There are some, experiments turn on and off. So Boraxino and Diabae are unfortunately turned off now. But then there are more experiments that are coming on. So it's been an automated operation since 2005. So basically they look for, if any two neutrino detectors actually detect a burst within about 10 seconds of each other, that is so rare, expected fake rate of 1 per century, they alert the world. Okay? Right. Okay, now, there's a little problem with this, which we've noticed, which is that if your fake rate is once per century, and you haven't seen a galactic supernova since 2005, you have a tendency to get messages from people asking you, are you still working? Right? Why haven't I gotten an email from you guys? Right? But on the other hand, this is partly a consequence of the fact that when SNOOS first came up, astrophysicists told the particle physicists, if you ever give us a false alarm, we're never going to believe you again. Okay? This is actually one of the consequences of that. Now, fortunately, astrophysicists have learned about statistics since then. So, we can, you know, actually people have realized that having a higher fake rate is actually useful. So, yeah, so you know, now we're looking at more like a fake rate once per month. Okay, that's what we're actually targeting. Okay, then, you know, if you're going to upgrade the system, then you can say, well, you know, can we also do more with the system than we did before back in 2005? So, you know, questions like, well, you know, where, you know, where might the supernova be? What's going on? You know, we were not able to answer these kinds of questions back in 2005, but with the more sensitive detectors and techniques, we should be able to make something of that. So SNOOS 2, there was a white paper several years ago, you know, about, you know, how we were going to upgrade this, and I'll just go through a couple of these points. I mentioned already the false alarm rate of once per month, which will be used for things like, yeah, proof of life, fire drills, etc. Provide, you know, also information in real time that might help observers later on. Also implementing a pre-supernova alert, so take advantage of the neutrinos that might be coming out of silicon burning, which might have, you know, at least for nearby stars, we might be able to get this. And then, yeah, develop a follow-up strategy to prepare the astronomy community. The network of detectors is potentially quite a bit larger, and actually some of these guys have already signed the MOUs, and we're sort of working on a bunch of the others. So there's KM3Net, there's, yeah, IceCube, Juno coming online, et cetera, et cetera. In terms of event yields, now remember, before it was 24 events. Now we're talking potentially thousands of events. Okay, and okay, now IceCube claims that they're going to see, like, you know, almost 1 million events. Little grain of salt, their background rate is also astronomical. Okay, so in terms of their statistical power, they're actually kind of about half of Super K, actually, Super K. Anyway, much more data, potentially, the next time we have a galactic supernova. So, you know, hopefully, a galactic supernova will actually happen while these detectors are on. Yeah, we'll have to see. Also notice the other thing that you see here, which kind of annoys me, is the fact that except for IceCube, there's nothing in the southern hemisphere. There is a tiny little neutrino detector that's going to get started up in Australia in the next few years, but it's a tiny one. Yeah, not too many other plans. You know, it would be great to encourage physicists in the southern hemisphere to sort of go in that direction. Anyway, okay. Then we have some of these other calculations, like rapid calculation of observationally relevant quantities. So that will include things like direction, estimates of distance, and whether there are some other things that have happened. So it depends on how. Of course, this depends upon actually these experiments sharing data in real time, which is not the easiest thing to manage, but actually can be done. This is an example of what you can do with electron elastic scattering at Super Kamiokande. The problem here is that the interaction cross-section is just a fraction of the inverse beta decay. So what happens is that the inverse beta decay, even though it's very interesting in terms of timing and all sorts of other things, it's actually a background where it comes to trying to point to where the supernova happened. So this is actually what their sort of map of events will look like. Kind of 10 kiloparsec supernova, 27 solar masses. The IBD events, the inverse beta decay events, they don't really give you any pointing information almost at all. Okay, so that's just a flat background. The electron elastic scattering will give you a little sort of cluster of events going in one direction. Okay, it's about 1/10 of the events. And from that, they are trying to infer the direction. They've done impressive work, however, getting this to work. And they're still developing algorithms. And they can actually do this in about 3.5 minutes. It's really impressive. And then localize that down to about 50 square degrees. You can also do triangulation. So if you compare the timings of different experiments, you can also sort of calculate, where it is in the sky. This is much less precise, but potentially faster. And also, doesn't depend upon one single detector being on, okay? Because detectors do go up and down. And so these are some of the sort of probability maps that we get. This is Super Kamiokande plus Juno plus LV plus Snow plus. So these are actually detectors that are either on already or will be on very soon. Yeah, okay, so time series matching, this is just, I don't remember actually what, well, yeah, if you get much larger detectors, so this is kind of a future plot, you know, you can actually localize to a much better extent. Yeah, and then if you get a nice sudden feature like that black hole formation, right? You know, so you get a nice cutoff, and then you know the statistical power of the triangulation is even greater. In which case, yeah, you can, you know, if just a neutron star forms, you get sort of this big localization area here. But then if it's a black hole, it's much more precise. Yeah. So okay. So that's direction. You can also combine this with the fact that actually red supergiants are not actually all that common. You can actually sort of, you know, look in the sky and start counting them. So that's what some people have actually done. They're sort of compiling these lists, and just having people point their telescopes and observe them, just to get sort of pre-supernova data, because these are considered to be the most likely candidates to actually explode. Yeah. Okay, and then yeah, pre-supernova neutrinos. Yeah, again, you know, can increase the warning time by hours. There is an experiment, CAMLAN, which has pioneered regularly publishing their sort of the significance of their inverse beta decay observations. Super Kamiokande has joined them in the last year, and Snow Plus is coming online, and Juno will do this too. Right, okay. We can also have an estimate of distance, just based on the neutronization, what we call the neutronization burst, where the initial stage of the collapse. So that's kind of a standard candle, where everything else in a core collapse supernova actually varies by the environment. At least this should be relatively constant. For the most part, people thought that this is kind of impossible. We might actually be able to do a little bit better and exceed people's expectations on that. And yeah, there are different schemes for doing this, which I won't go into details on. Why is this actually kind of relevant? I mean, why do we particularly care about the distance? Because as long as we got the, you know, pointing out into the sky, isn't that enough? Well, a couple things. One is that, you know, with those maps of candidates, you know, we know kind of how far those candidates are, so you can actually narrow down quite a bit if you have a three-dimensional localization. But the other thing is that the distance, even without a direction, can actually tell you a little bit about the observation strategy you need. Because we're sitting here about 10 kiloparsecs, actually 9 kiloparsecs away from the center of the galaxy. On the other side of the center of the galaxy, or at least anything on the other side of the galaxy is going to go through a huge cloud of dust to get to us. Which means actually that a lot of the optical stuff may get absorbed on the way. Okay? So we will observe quite different things depending on where in the galaxy the supernova actually ends up being. And you can tell some of this just from the distance information. So, you know, you might actually sort of concentrate more on infrared observations rather than optical, you know, other kinds of things. Okay. So yeah, all these things then feed into the follow-up, and you know, here we sort of recruit a bunch of communities. You know, there are a lot of observers around the world, along with a lot of amateur observers. Okay, just people with telescopes in their back gardens, and they've been doing this for a long time, actually. So we've been working with those communities to try to figure out how to optimize the search, right? Because if you get the neutrino burst, nothing happens for a while, right? You don't get the light until half an hour to 48 hours later. So you get a bunch of people staring up at the sky waiting for something to happen. How do you optimize that process? Okay, it's not a very trivial sort of question. Right, so yeah, neutrinos from a galactic core collapse supernova could yield a rich harvest of physics and fundamental questions, including astrophysics as well. But they're very rare, so we really have to make the most of the opportunity. So neutrinos are sort of like that starting gun to get the most bang out of the next supernova, and so that's why we have SNOOS. So this has been in operation since 2005, but we're actually trying to add to that information right now, and So we have students working on these kinds of questions, including some that are sitting here in the audience. So yeah, sorry for probably going a little bit over time. Any questions? Yeah.
In the beginning of the lecture, you mentioned that there needs to be a quadrupole moment in the mass distribution for us to observe gravitational waves. Could you elaborate on why that is?
Fairly simple answer is that is that a graviton is spin 2. So you need to have something coupled to a spin 2 field. Yeah, you can't do that with, I mean, dipole is spin 1. You know, nice spherical symmetry just gives you spin 0. Right? Did that answer make sense? That's kind of like that's almost like the kind of question, that's the kind of answer that you get after B2, I think. But it's probably the simplest version of the answer. So.
How would you use the neutron detectors to detect neutrino mass? Like the different neutrinos mass?
Several different ways. One of them is just arrival times. Okay, because they will, they potentially travel at different speeds. And there are things connected with oscillations, but, and in fact, even the CP violation in that context, because again, it's going through this extremely dense matter field, and you get these kind of mixings along the way, and all that. Yeah, unfortunately, trying to do it that way, very difficult, and we'll probably argue about it for about a decade before we settle on an answer. Okay, that would be my estimate. But yeah, there are several paths by which we could potentially do that. The simplest one being arrival time, but even that is actually going to be complicated by the fact that there aren't, limited data, almost no matter what you do, and also, yeah, then the clock synchronization becomes really critical, and I mean even more critical, plus backgrounds. Probably if I sit here for about 5 minutes, I'll think of another 5 different ways that could be wrong. Yeah. Other questions? Go on.
Yeah, so I think like until like supernova burst, we'll just have this neutrino burst, and I'm thinking about like after supernova they overlap a neutron star, and actually we know like little thing about neutron stars. So can we just tell the property of the neutron star from the neutrino burst?
Sorry, can we what the neutron star from the neutrino burst?
So like after the supernova, we'll have like a neutron star left as equal. So can we just tell the property of that neutron star from the neutrino burst?
You can tell various properties from, or at least people think you can tell various properties, including things like the equation of state, from the later time development of the neutrino luminosity. But of course, that depends on us being close enough that we will actually continue seeing the neutrino luminosity beyond that, because obviously neutrinos with a very low cross section, the burst is probably where, I mean, within about 10 seconds, that's actually where you get most of your neutrinos. So, yeah, obviously, if you're talking about the equation of state of the neutron star, or if you want to talk about the properties of the neutron star, you want to talk about it sort of in its having settled down to actually be a neutron star. Most of this stuff that I'm talking about with regard to the burst, also very interesting. It's actually more like the proto-neutron star stage. So things are still kind of boiling. Did that answer your question? Okay. Anything else? Okay.
In one of the initial slides, you had that graph between like neutrino flux and the energy scales which they are found at. I have a question on that. Very big.
Let's see.
Yeah,
this one. Okay.
Why do atmospheric neutrinos have energies in giga-electron volts, or what high energy processes do we have in the atmosphere that can produce that?
These are usually protons and muons colliding in the atmosphere and producing neutrinos in the atmosphere, in the upper atmosphere.
So those protons have really high energies, so that is how.
Yeah, those are the actual causes, the primary cosmic rays, and the neutrinos Okay. Well, thank you very much. I hope that wasn't too, whatever, non-interruptive or something. Sorry, the usual joke about neutrino physicists is that they don't go in.